Okay, let's try to understand traction. Okay. Traction is very important concept. If this concept is clear, the concept of stress is will be very easy to understand. And note that the stress, I know like the for FE engineers, okay, for mechanical engineers, the stresses are very difficult concept to visualize. Like we don't know how, we know the stress components, different stress components, but we don't know the physical significance of the stresses. Okay, we can't visualize how the stress looks. And after this section of this concept of stresses, I am confident that you will be you will be having very clear understanding of stresses, and you will be able to visualize the stresses. And this is very helpful. Okay. uh, it is not that only FEA equations are enough to understand, only pre-processing and solving. The post-processing part is more important than pre-processing and solver, right? As FEA engineers, we need to understand and interpret the FEA results, and that's where the concept of stress is. If the fundamentals of stress visualization and concept of stress is very strong, you will be able to interpret FEA results very efficiently, and then the results will make sense. Okay, the stress results will make sense. Okay, so let's understand the concept of traction first. Okay, let's take this solid body which is subjected to external load, and it is constrained at some region. Okay, so it has infinite number of continuum particles or points. uh, this is a deformed position. Okay, after external load, let's take this is how it deforms. Okay, uh, now we want to understand, like when the body is subjected to external load, how it behaves. Okay, that means how it resists. We want to understand the internal forces. Okay, so internal forces are generated, they are nothing but resisting forces to the external loads. So we want to understand the internal forces. So for that, let's take this cut section here. Okay, and if I draw this further, okay, this cut section will divide or split this body into two different bodies. Okay, just for understanding. So let me draw that. Okay. So when we take this section here, uh, as we know, like entire all the points in the body are subjected to, or they resist, they generate the internal forces, right? So if we take the section here, we'll get some forces here, okay, at each and every point. Okay. They could be in any direction with respect to this cut section, this section. Now this left hand side will impact the forces on right hand side surface, semi and vice versa. So both the surface will impact the forces on each other. Okay, and the corresponding point, like on left and right hand side, will have equal and opposite direction of forces, internal forces. So if I want to explain that, let's take this left hand side surface and right hand side surface. Okay. This is surface normal. Okay. Always the surface or cut section is defined by its normal. Okay, so let's take this is a surface normal, and obviously this is also surface normal. Both are in same direction. And let's take at this point, okay, we want to see the internal forces. So let's take it is something in this direction t, and since both points are same, uh, this internal force will be equivalent in opposite direction t. So that's what I want to say, like uh, the corresponding point on left and right hand side will be having same internal force, okay, but in opposite direction. And this remember that this traction or this internal force, not traction, we are not yet come to traction. This internal force can act in any direction, okay? It is not that it is always normal to surface like in direction of n, okay? It can be in any direction, okay? So with this now let's define a traction. So traction is defined as intensity of force, intensity of internal forces. So let's try to understand this. Okay, we want to find the intensity of internal forces. These are the forces here. Okay, let's take same cut section. Okay, and we want to find the intensity of force at this point. Okay, so remember that let's recall our assumption in quantum mechanics. We said that uh, at microscopic level, sorry, at macroscopic level it is a point, but when we zoom into it or at microscopic level we can define the finite size of that particle or point, okay? So in microscopic level, let's take the dimension or size of this is delta a. So delta l is infinitesimal area, right? So infinitesimal means very small, okay? In microscopic level it becomes zero, okay? And at this point let's take the internal force is delta f. So we can say the intensity of force I is equal to delta f by delta a uh, at microscopic level. But we are always interested in macroscopic level. So when we put limit that this area becomes, okay, zero, then it becomes a point, right? So when we say like this infinitesimal area delta a tends to zero, this will become point, okay? So delta f by delta a, and this is our traction. This is called traction. Okay, now let's see some properties of this traction. Okay, so traction t is function of x and n. What is x and n? Traction depends on position, okay, or location. That means at each location there is a different traction or different intensity of force. That is very clear. So if you have worked with finite element analysis earlier, you know that in some softwares we can take the cut section and see the free body diagram, right? And you would have observed that when you move that slider in your FEA software, you will see the force free body diagram of that force, okay, the resultant force on that cut section will change, okay, when you change the position of the slider, okay. And even on that section, at each point there is a different intensity of force, that is obvious. So it depends on position, that is x, okay, and it depends on n. So what is n? So n is a reference surface normal, reference surface normal. So why it depends on n? Okay, so let's try to understand this. Okay, let's take this particular point which we are talking, okay, and we have already taken one surface here like this, and we said like this is a surface normal, and we have this t, right, traction. Now at this point we can have infinite number of infinite number of reference surfaces, right? So infinite number of surface normals. So if I take a different cut section, let's take this is the cut section, okay. uh, about this surface there is a different traction, okay. If I take another different surface normal, about this surface I will have different traction, okay. That means the traction depends on position, but at that position it also depends how we take the surface normal or surface normal, okay. That means we can define traction as, so I'm just now refining the definition of traction. So traction is defined, okay, at a point, at a point with respect to, we have to add something with respect to reference surface normal. So I will just say surface normal, okay. So t is function of for x and n, okay. If n is different, the traction will be different at that position x, okay. Because at a point we have infinite number of surface normals, okay. That means we can also say that traction at a point has a infinite number of traction vectors, okay, depending on which surface normal we take, okay. So some more no, properties, let's see, okay. Let's try to understand traction more clearly, okay. So traction is vector. How? Because we know the traction is derived from the force, right? It is intensity of force at a point, okay. So if force is vector, traction is also vector, okay. So like let's take this one, uh, the point here in this body, this point, okay. Let's take this is the normal, this is a traction. So always we define it as a Tn because traction is associated with surface normal. Okay, so let's from now we'll say Tn. So if I have this body uh, in this coordinate system x, y, and z, okay, the Tn, the traction can be decomposed. Okay, let's say this is a Tn. We can decompose this traction into three different components. So Tn or Tx, Ty, and Tz. So we can say traction is vector, and second property is the unit of traction is Newton per mm square. So how the pressure also has a unit of Newton per mm square. Okay, but there is a difference. Pressure is scalar, whereas traction, as we said, is a vector. Yeah, because pressure is always normal to surface. So this is a fundamental difference between pressure and traction. And since we say it is a vector, we can say Tn. We can represent vector as three components: T1, T2, T3. Let's take a 1, 2, 3 convention, not XYZ. Hope the understanding of traction is clear.